Hi everybody, this is going to be our first lesson video for calculus, but before we get started I just wanted to say that I do miss you and I love you, and I'm hoping that these videos will be of some good to you. There's just no way that we're going to learn the rest of calculus this year, so I'm just going to hit the highlights and tell you the most important things and do these videos maybe once a week, possibly twice, but I'm not going to overburden you with work. I know you have 7 classes to worry about, and mine is just one of those 7, so I'm not going to give you a ton of work. I'm just going to give you what I think are the most important parts. So we are going to begin today. So if you haven't printed out the note sheet yet and the worksheet, you might want to stop and do that. I also included the unit circle as well as the anti-differentiation rules. So I'll give you a second. You can always pause and do that before we get started. All right. So before we left for break, we were studying the Riemann sums, and I wanted to remind you what that looked like. So here is just an example. Remember how we took a function and graphed it over a certain interval, and then we made the rectangles and then found the area of each rectangle? That was a very tedious process, but what we were doing is finding the area under the curve, between the curve and the x-axis. So what we were actually doing is finding an integral. So I'm going to show you how you can find the answer and the exact answer without having to draw the rectangles like we did in class. So on the note sheet, you'll see that there is a new notation that you might not have seen before. And I want to preface this by saying that it doesn't look so great on the document that I sent. So I create all of my notes and worksheets on Microsoft Word, which has a really good program in it for equations. But in order to put it into Google Classroom, I had to convert my document to a Google document, and when I did that, the equations kind of look a little differently than they normally do. So let me show you what I mean. So on your paper, I'm gonna go ahead and get my whiteboard now. So let me put this down. Okay, so on your paper, you'll see a weird looking symbol that is supposed to be an elongated S, but it doesn't look very great on the paper that I sent you. So it should be like an elongated S, kind of like that. And then there should be a number here, like A, and a number here, like B. But on the paper, it kind of shows it as a strange symbol, and it's got the A here and the B up top. It's supposed to be like this, but it just didn't show that way on the Google document. But anyway, you're gonna have, this is called an integral symbol. You're gonna have a number here on the bottom, that's called the lower limit. And on the top, you're gonna have what is called the upper limit. And then there will be some function over to the side, that can be just any function. And then you'll see it also has dx, and that just means that the variable in that function is x. So this symbol was created by Leibniz. He was the one of the first creators of calculus. And then there was another person named Isaac Barrow who later discovered integrals. And basically an integral and a derivative are inverses of each other, so that means what one does, the other one undoes. So kind of like when you were first starting math, you learned that addition and subtraction are inverses of each other, and multiplication and division are inverses of each other, and so on. So all the way up through calculus, here we are, inverses are derivatives and integrals. Okay, so let's look at some of the examples. So there is something called the fundamental theorem of calculus. So it's on your note sheet, but when you want to solve something like this, what you will do is you will find the antiderivative of the function, and the antiderivatives are found by using the anti-differentiation table that I attached to the lesson. And we went over antiderivatives before we left school. So it's noted by a capital F. So that stands for the antiderivative of whatever function this is. So you would evaluate that antiderivative at B, and you would also evaluate it at A. And remember, A and B are these numbers over here. And then you would subtract those values. So that is called the fundamental theorem of calculus. It is the most important concept in calculus. So I knew I had to cover this because this is like a biggie. So we're going to look at this. So basically what this does is it allows us to find the area between the curve and the x-axis without doing the triangles that we did in the Riemann sums. Okay, so let's take a look at some actual examples. So I'm going to go through just like I normally do and look at each of the questions. Now keep in mind this is a video, so you're welcome to pause it and rewind it and do all that you normally do with videos. And that's kind of nice because when I'm teaching in class, you can't pause me or rewind me or play me again. So that's kind of the beauty here, is that you can do that with a video. So I'm hoping that you will take advantage of that and stop it if you need to catch up, or rewind it if you missed something I said. So here we go, number one. So number one says that we are going to find the area of the region between the curve y equals x squared and the x-axis in the interval from 0 to 1. Okay, so this might sound familiar because we did this before we left for break. It was just that we were using Riemann sums to do that. So I'm having to look at a document on the computer while I do this, so sorry if I'm kind of juggling together. Okay, so what we can do is take that problem and turn it into an integral. So you're going to use the elongated S, which should be something like that. So the lower limit would be the 0 in the interval. The upper limit would be the 1. And then the function to the side would be x squared dx. So that is the statement in number one, written instead as an integral. Okay, so the first thing you're going to do is find the antiderivative of the function x squared. So we covered this before we left for break. So the antiderivative of this function is, so you might need to consider or look at the anti-differentiation rules that I sent you in the attachment. But this is just a polynomial. So what you do is you create a fraction. There would be 1 in the numerator. And whatever the exponent is here, you add 1 to that. So think of this 2. If you add 1, that would be 3. And then you have your variable x. And then you use this number here plus 1 again. So it's 3. So it would be 1/3 x cubed. And then if you notice on the table, it says to put plus c. And we discussed this before we left school, that you could add any constant to that, and that would be the antiderivative. Now, when we're doing these problems, we want to use the simplest antiderivative. So we could put anything over here for c, but why do that to ourselves if we don't have to? The easiest number that I could plug in here would be 0, which would mean we wouldn't have to include it at all. So we're just going to use this right here as f. Oops, I forgot the 3 there. Okay, so we're going to plug that in to the fundamental theorem of calculus. Okay, so we're going to find the antiderivative evaluated at 1, and then we're going to subtract the antiderivative valued at 0. So that should be 1/3 x cubed. Okay, so that means we're going to plug in 1 to 1/3 x cubed. So that would be 1/3 times 1 cubed, and then minus 1/3, sorry, I didn't look right, 1/3 times 0 cubed. And then we will just calculate what that is. So you're welcome to use a calculator. I won't know if you're using a calculator or not, so that's fine. But this is an easy one. 1 cubed would be 1. Multiplied by 1/3 would be 1/3, subtracted by. So 0 cubed is 0. 1/3 of 0 is still 0. So then 1/3 minus 0 would be 1/3. So there's your answer for number 1. The answer would be 1/3. So the idea is, with this, if you had to do this by Riemann sums, just as a refresher, remember you made the graph and you drew all the triangle or rectangles, and then you had to do all those calculations. I know you all hated that. So this gives you the same answer as we would have with the Riemann sums. So much simpler way to do so. So that's number 1. So pause that if you need to catch up, but that's number 1 complete. So we're going to go on to number 2 next. All right, so number 2. So number 2 says we're going to be evaluating an integral from 0 to 2 of e to the x plus x dx. Okay, so we are going to first need to find the antiderivative. So just do that over to the side. Capital F represents the antiderivative. So e to the x is one of the special cases that the antiderivative is the same thing. So in this case, you would not change e to the x. This is in the table that I gave you as well. So e to the x does not change. But we have to see what happens with this x. So keep in mind it's just a polynomial. So we're going to use the rule that we did in the last problem. So you're going to write it as a fraction with 1 in the numerator. And in the denominator, you have to consider that this is really like x to the first power. So you add 1 to it. So 1 plus 1 would be 2. And then the variable, and then the same exponent that is down here, 2. So your antiderivative would be e to the x plus 1/2 x squared plus c. Now remember, c can be any number, so let's make it easy on ourselves and just think c is 0, and then we won't have to do more complex calculations. So we're going to be using this as the capital F, the antiderivative. So now we're going to do the fundamental theorem of calculus. So we're going to do the F2 minus F0. And remember, these numbers just come from here. This is 0, and that's 2, so that's the 2, and that's the 0. So you're plugging it into the fundamental theorem of calculus. Okay, so we're going to take this and plug in 2 first. So that would be e squared plus 1/2 times 2 squared. And then we're going to do e to the 0 plus 1/2 times 0 squared. And we're going to do those calculations. Now, e squared is a constant number. If you put that into your calculator, you would get a decimal. So I'm not going to do that. We're just going to leave that as e squared. That is a constant number, though. So let's figure out what this is. So you would do 2 squared first. That would be 4. And then 1/2 of 4 would be 2. So that first part would be e squared plus 2. That's like this calculated. So now we're going to see what this part is. So go ahead and bring down the subtraction sign. E to the 0 power. Now this number is different in that there was a rule that you all learned in algebra a long time ago that any number raised to the 0 power is just 1. So we're going to replace e to the 0 with 1. And then over here, you would figure out 0 squared first. Of course, that's 0. And then 1/2 of 0 is still 0. Okay, so we would still have the e squared. We would still have this 2. And then, of course, 1 plus 0 is 1. So you would just subtract 1. And then finally, we would do 2 minus 1 is 1. And this is a constant number because, again, e squared is a decimal. But I'm just not going to put that in the calculator. So it's e squared plus 1. And you can give your answer like that if e is involved. So final answer for number 2, e squared plus 1. So again, you can pause it and restart if you need to catch up. Okay, so number 3. I wish I had a printout of this so I wouldn't have to keep looking at my computer, but don't have a working printer at home right now, so having to go back to my laptop and look to see what the next problem is. All right, so number 3. So it's called the integral from 1 to 3 of t cubed plus 3 dt. Okay, so this one, notice, has the variable t. It's going to work out the same way. I just wanted to show you that it might not always be x. You might see other variables. So t is a common one. So notice that because that's a t, then over here it just says dt. So that means that the variable in the problem is t. Okay, but we're going to do exactly the same thing. So we're going to do the antiderivative first, capital F, and this is a polynomial, so we're going to follow the same rule. So it's going to be a fraction, 1 over whatever the exponent here is, 3. We're going to add 1 to that, so that would be 4. And then we'll have the variable x, and then add 1 to the exponent, so 4. So for the first part, t cubed would become 1/4, I should use a t to the 4th. And then the 3, you would just use the plus sign. And then here, instead of 3, it would be 3t. And then plus c. Sorry, I'm having to reach way over there, so it's not as clear on that side. But yeah, that would be the antiderivative. And you can just think of c being 0 to make it easy on ourselves. Okay, so we're going to take this antiderivative, the 1/4 t to the 4th plus 3t, and we're going to plug in the numbers 3 and 1. So we're going to be finding the antiderivative evaluated at 3 minus the antiderivative evaluated at 1. Okay, so we're going to plug in 3 to that. So the first part would be 1/4 times 3 to the 4th plus 3 times 4. And over here, we would plug in 1. So it'd be 1/4 times 1 to the 4th plus 3 times 1. And then we'll calculate that. So again, you can use a calculator if you like. I'm not going to juggle a calculator with holding this whiteboard, so I'm going to do it by hand. So 3 to the 4th power, if you don't know that, it means 3 times 3 times 3 times 3. So that's 81. So that would be 1/4 times 81. And right here, 3 times 4, of course, is 12. And then over here, 1 to the 4th is 1 times 1 times 1 times 1. So that's 1. So then that would be 1/4 plus, and then 3 times 1 is 3. Of course, it'd be much easier to do this with a calculator, but I'm going to do it by hand. So 1/4 times 81 is 81/4. And then I have to add 12 to that. So I have to get a common denominator. So if I use a 4 in the denominator, 12 would be the same thing as 48/4 minus. And then 1/4 plus, if I get a common denominator over here, it would be the same thing as 12/4. So then we can now add 81 plus 48 would be 129 over 4. And over here, 1 plus 12/4 would be 13/4. And then 129 minus 13 would be 116/4. And if you divide 4 into 116, of course you can use a calculator. That'd be 2, 8, 3, 6, 29. So final answer for number 3 is 29. Again, you can pause it if you need to and restart. Okay, so moving on to number 4. So number 4 is the integral of 0 to pi of cosine of x. Okay, so first of all, we have to find the antiderivative of cosine of x. So you would first look at the table of antidifferentiation rules that I attached. So the antiderivative of cosine is sine of x. And then you'd put plus c. But we're going to keep this easy and make c 0. So you're going to be evaluating the antiderivative at pi, and then you're going to subtract the antiderivative at 0. So we're going to be plugging in pi over here for x. So that would be the sine of pi minus the sine of 0. These numbers come from here, pi and 0. So you would need to look at the unit circle, and I believe I attached that too. You can either use that or use the unit circle that I gave you in class. So if you look at the unit circle, you'll find that the sine of pi is 0. And then if you look at the circle, you'll see that the sine of 0 is 0. And then of course 0 minus 0 is 0. So final answer for number 4 is 0. Feel free to pause and restart if you need to catch up. Okay, so here's number 5. So we're first going to look for the antiderivative. Now this one is a square root, and just to refresh your memory, a square root can be rewritten as an exponent with a fraction. So a square root is x to the half power. So that would be the same thing as square root of x. So we're going to use our antidifferentiation rule that I sent you a copy of. So you're going to write it as a fraction, 1 over, and you have to add 1 to the exponent that you started with. So 1/2 plus 1 would be 1 1/2, which is the same thing as 3/2. And then x to the 3/2 power plus c. Okay, so when you have something like 1 over 3/2, that means the reciprocal of 3/2. So it would be the same thing as the reciprocal, which would be 2/3 x to the 3/2 power plus c. And keep in mind we're going to use c as 0 just to make it easy on ourselves, and evaluate this right here at 9 and at 1, and then subtract the 2. So it will be the antiderivative evaluated at 9 minus the antiderivative evaluated at 1. So you will be doing 2/3 times 9 x to the 3/2 power minus 2/3. Oops, wait a minute. Sorry, not 9x. I'm plugging 9 in for x. Sorry about that. So I'm going to be doing 9 to the 3/2 power, and then over here 1 to the 3/2 power. Okay, so you're welcome to use your calculator, but if you were to type in 9 raised to the 3/2 power, you would get the answer 27. And over here, if you would plug in 1 to the 3/2 power in your calculator, you would get 1. And then if you do 2/3 of 27, that would be 18. And then 2/3 times 1 is 2/3. Now, if you didn't use a calculator, you would have to find a common denominator. So with a denominator of 3, 18 would be, let's see, 18 times 3 is 4 to 54. I'm doing old school math now. So 54 thirds is the same thing as 18 minus 2 thirds would be 52 thirds. So your final answer is 52 thirds. Now, if you're doing this on your calculator, you're going to get a decimal as an answer. So go under math and pick fraction, and you should get your decimal to a fraction like I have. So that goes for any of the problems. If you're getting a decimal, go to math fraction on your calculator and it'll change it. All right, so that should be the final answer for number 5. You may need to pause this and catch up if you didn't write all that down. Okay, well, we only have one more problem to go. Okay, so for number 6, last problem is the integral from, gosh, I have to move the cursor on my computer real quick, sorry. We're going from 1 to 2 of v cubed plus 3v to the 6th over v to the 4th dv. Okay, so another variable v. That v just means this is going to be v over here. No difference though in how we solve the problem. Okay, so this right here looks complicated right now, so we can simplify this a little bit. That will help us to get the answer to this question. So let's work on this part first. So with fractions, if you see like 2 different terms in the numerator, but the denominator is just one term, you can separate this into 2 fractions. So that's what I'm going to do. I'm going to change it to v cubed over v to the 4th, and then 3v to the 6th over v to the 4th. That's the same thing as that. So the reason I did that is that I can simplify each piece. So like this part right here can be simplified, and so can this. So when you were studying exponents in algebra, you learned that when you're dividing, you can subtract exponents. So v would still be the variable, but 3 minus 4 would be -1. And then over here, the 3 would still be there, but subtract the exponent. So 6 minus 4 would be 2. Now, if you ever see a negative exponent, you rewrite it as a fraction. So it would be 1 over v. And then this part would still be 3v squared. Okay, so then that would be the same thing as this. So this one just took a little bit of work to get it more simplified. So I haven't taken the antiderivative yet. This is just the simplified form of this. So I kind of ran out of room, so I'm going to erase this in a second. So if you need to catch up, stop it now, and then I'm going to erase it. Okay, so I'm going to replace what was there before with 1 over v plus 3v squared dv. Same thing. Okay, so then we are going to get to the antiderivative. So if you look at your chart of differentiation rules, this one is a special case. 1 over v is a natural log. So if you look at your chart, it says it's the natural log of the absolute value of v. That is the antiderivative of this. And then we would do this just like a regular polynomial. So 3 would be in the numerator. In the denominator, we would add 1 to the exponent, so that would be v cubed. Or sorry, 3. Not v, 3. Add 1 to the exponent, so that's 3, and then this would be v cubed. Okay, so our antiderivative would be the natural log, absolute value of v, plus, now 3 over 3 is just 1, so it would be v cubed plus c. Okay, so then we're going to evaluate that at these two numbers. So we're going to be evaluating that antiderivative at 2, and then subtract the antiderivative evaluated at 1. So we're going to be plugging in 2 here and here. So it's going to be the natural log, absolute value of 2, plus 2 cubed. That's the first part. And then the second part will be the natural log of absolute value of 1, plus 1 cubed. Sorry, I was kind of writing there and it made it not straight for you. Okay, so that's how it would look. Okay, so the absolute value is there just to ensure that you don't get a negative answer there. So if this had been a negative number here, and that became a negative, the absolute value would take care of that. So you can take the absolute value off at this point. So it'd be natural log of 2 plus 2 cubed would be 8 minus, same thing here, take off the absolute value now, natural log of 1 plus, and 1 cubed would be 1. Now the natural log of 2, if you were to put that in your calculator, it would give you a decimal, so I'm not going to change that to a decimal. I'll just keep it natural log of 2 plus 8. But over here, this one is a special case. If you were to type in natural log of 1 on your calculator, you would get 0 as the answer. So it's not a decimal, it's the whole number 0. So we're going to have the natural log of 2 plus 8 over here. And on this side, 0 plus 1 is just 1. And then that would be the natural log of 2 plus 7. And the natural log of 2 is a decimal, so if you added 7 to it, it would be another decimal. So we're just going to keep it simpler and just leave it in this form. So it'd be natural log of 2 plus 7. Okay, so that is the full number 6. Of course, that was the toughest one of all because we had to do several things at once. So pause it and catch up if you didn't quite get all that. Okay, so we're done with this lesson, and I want y'all to know that I understand that was a lot to take in at one time. So if you have questions, you're welcome to reach out to me via Remind or my Google Voice number. The number again is 863-417-9602. You could email me. We could even do a Google Meet if you want to see each other and talk through the problems. Whatever will work for you, I'm all for it. And until next time, I'll talk to you later, y'all. Bye-bye.